The third colligative property is depression in freezing point. Depression in freezing point. Depression in freezing point. Actually, this is having a lot of application. When you go to a hill station, you can see the diesel. When the temperature of the environment is lower, the diesel become just like wax. So it can be prevented if you add an anti-freezing agent into it. So if you add any anti-freezing agent into it, it will not freeze. Like that in radiator water, nowadays we add ethylene glycol or propylene glycol as an anti-freezing agent. It prevents the water from freezing. So that's the main application of the depression in freezing point. So you will see pure solvent has a definite freezing point given by the expression, given by the graph. This is solvent, and now we are going to lowering the temperature. At a particular state, at a particular temperature, it changes into solid. So this is T1. So T1 is a freezing point of solvent, and this is a solid state. And again you are reducing the temperature of a solution. You will get another temperature that will be always lesser than T1, and that is given by the letter T2. Here you have vapor pressure and here you have temperature. So the T2 is a freezing point of solution. Here T1 is greater than T2. So the difference is given by delta TF. Delta TF is equal to T1 minus T2. So T1 minus T2 is called the delta TF, and delta TF is called a depression in freezing point. Depression freezing point of solvent. And here also the same relation. Delta TF is proportional to M, and M is called a molarity. You can substitute delta TF is equal to Kf into M. So Kf is a constant. And that constant is known as a molar depression constant. Its other name is called a cryoscopic constant. In the previous case we have seen it is a molar elevation constant. Here it is molar depression constant. And you substitute for every solvent a definite value for Kf. Every solvent has a definite value for Kf. Kf is called a molar depression constant, and that Kf can be calculated using the expression RT0 square divided by small LF into 1000. And what is this LF? LF is latent heat of fusion per gram of the solvent. So this LF is latent heat of fusion per gram of solvent. So this is Kf. So you can calculate LF by capital LF divided by molecular weight. So what is capital LF? Molar latent heat of fusion of solvent. That means the heat required to convert 1 mole of solvent into solid state, that is molar latent heat of fusion, or solid state to liquid state, that is molar latent heat of fusion. So that capital LF divided by molecular weight, you will get small LF. Substitute small LF here, you will get the value of Kf. And every solvent has a definite value for Kf. And after this you substitute here, delta TF is equal to Kf into M. So M, you know, delta TF is equal to Kf into Nb divided by Wa into 1000. That is the expression for molarity. Then Nb is equal to delta TF is equal to Kf into, for Nb you substitute Wb by Nb into Wa into 1000. So this is a final expression for depression in freezing point. So using this expression you can calculate delta TF, and substitute here delta TF, you can calculate T2. Then what is T2? T2 will be equal to T1 minus delta TF. Remember that in the previous case we have seen for boiling point T1 plus delta TB, but here T2 is freezing point of solution, is a lowering of freezing point, so we have to deduce, we have to subtract from T1. T1 minus delta TF, you can calculate T2, and at the same time you can calculate NB. NB also calculate. NB is molecular weight of solute. Can be calculated. Molecular weight of solute. So these two can be calculated using this expression, and this is the expression, and delta TF is equal to Kf into WB into 1000 divided by MB into W. So this is the third colligative property, depression in freezing point.